Today we're going to be talking about just general water quality, the importance of routine lab testing, how water quality is going to help you to make nutrient decisions, and how lab testing can really help you improve on your nutrient solution management over time. A little bit about me. I'm the CEA Technical Specialist here at J.R. Peters. I have a bachelor's in horticulture from Mississippi State University, and then I went on to get a master's in horticulture from the University of Arkansas. I've done a lot of things sort of in the general horticulture space, including whenever I was in undergrad, working in horticultural retail at a garden center, working in floral design. After that, I did some landscaping, public gardening before transitioning to graduate school, where my research really focused on nutrient management in recirculating hydroponic systems. And while I was there, I also did a good bit of teaching. I TA'd a couple of courses on hydroponics and greenhouse production. And then I also was in charge of sort of guiding our interns through greenhouse work study courses. And I co-authored a few eGrow edible alerts, if you're familiar with those. So, kind of have a good background in just helping people with the bare bones basics of getting started with this type of thing. So the topics that we're going to be covering today, first we're just going to define basic parameters of nutrient solutions, the main things that you're going to want to be aware of and to look out for. Then we're going to talk about general water quality and what that means for getting started, how that's going to help you select a fertilizer, and then how to manage nutrient solutions over time, depending on the type of hydroponic system that you're working in. And finally, the importance of regular and routine lab testing, how that can help you with getting started and how it can help you manage your solutions over time. So these are going to be the basic parameters that you're really going to want to be mindful of and keep an eye on over time, not only when you're first getting started and mixing fresh nutrient solutions, but also as you continue to use that solution. The first is going to be pH and then alkalinity. And then we're also going to look at EC, which stands for electrical conductivity, and the milligrams per liter of individual nutrients in solution. So this chart here is an example of our lab results that we routinely send out from our lab when we test water and nutrient solutions. It lists all of these parameters plus a few extra things. So the first one that we're going to be covering is pH, which you'll see is the second from the top on all of our lab results. pH is a measure of the hydrogen ion concentration in a solution. It's a lot of people refer to it as the acidity or basicity of your solution. pH ranges from a scale from 0 to 14, but 7 is going to be pretty much true neutral. Many pure water sources like RO or deionized water are going to have a pH pretty close to neutral, somewhere between 6 and 7. That's just the nature of having a pure water source. And this is great because optimum nutrient solution pH for most CEA and hydroponic crops is going to be between 5.5 and 6.5. That's going to be the range that you're really going to want to keep your nutrient solution at. But really, if you want to really narrow it down, 5.8 to 6.0 or 6.2 is really optimum. And so you can see on the chart here, that's where all of the essential elements for your plants that they're going to need to take up are going to be the most soluble. So they're going to be the most available to your plants at that range. And outside that range, you're going to run the risk of nutrient deficiencies, things not being quite as soluble. And also, if your solution gets too acidic or too basic, you also run the risk of just physical damage to your plant roots, as they won't be able to, take up nutrients and they'll burn a little bit too. So moving past pH, we're going to talk about alkalinity. Alkalinity is related to pH, but it's not the same. They do measure two different factors, but they are very closely related in solutions. Alkalinity measures the buffering capacity of your water. So that's really important for determining how quickly your pH is going to be able to fluctuate over time. A really low alkalinity, your pH can swing pretty wildly and very quickly. But a very high pH or a very high alkalinity, you may struggle to get your pH to change to where you need it to be. Typically, for most water sources, the higher pH, the higher your natural pH is, the higher your alkalinity is going to be. So like I said earlier, pure water sources like RO, rainwater, DI water, they're going to have near zero alkalinity. It's going to be very low, even though, your pH is probably going to be closer to 6 or 7. So if you have a very low alkalinity, you may need to add something additional to your nutrient solution to help increase the buffering capacity so that your pH won't change quite as drastically, and you'll be able to manage it and keep it in that necessary range for a longer period of time. The next factor we're going to talk about is electrical conductivity. This is the measure of total soluble salts in solution. So whenever we say salts, we don't mean salt like sodium chloride, like table salt, like you're going to think of. It's going to be when we say salts, what we're really talking about is charged ions in solution. So soluble salts in solution is going to be a great estimate for the general fertility of your nutrient solution, especially as you mix up fertilizers. On the fertilizer label, usually it will list what the expected EC is going to be at a certain mixing rate. So you can use EC to double check your mix, make sure that you were mixing correctly and hitting targets that you wanted. But it doesn't tell you the individual ion concentrations in solution. So when you mix up a fresh mix, you can double check to make sure that you were hitting your, say, your nitrogen target based on the EC of your solution. But over time, over a couple of days or weeks, just because you're hitting that same target EC, that's not going to tell you a whole lot about the specific individual elements that are in the solution. For that, you're going to need to do actual lab testing to look at and break down what specifically is in your solution. Soluble salts is measured in a couple of different units, but for the most part, you're going to see it in millisiemens per centimeter or decisiemens per meter. So these convert to the same thing, so the number is going to be the same. But that's just what that stands for. Your typical nutrient solution EC after you add fertilizer is probably going to be between 1 and 2.5 for most hydroponic crops that you're going to be growing. There are some really heavy feeding crops that are going to prefer a higher EC, probably closer to 3. But for the most part, like leafy greens and herbs, most vegetables, you're going to be around 2 or below. So one question that we do get a lot is, what is the difference between EC and TDS? Because there are handheld EC meters that we definitely recommend that you use to check your nutrient solution on a regular basis. But some of those meters measure TDS instead of EC. So TDS stands for total dissolved solids, and it's not the same measurement, but it is an alternative. So you can convert between TDS and EC, but they are measuring technically different factors in your solution. TDS is usually measured in parts per million as opposed to the millisiemens per centimeter that you're going to see with EC. TDS has become really popular with cannabis growers specifically. They're really accustomed to using that value. So that's where it can cause a little bit of confusion, not knowing whether you're measuring EC or TDS. And then, there's your 500 scale, your 700 scale. So converting between TDS and EC can frequently be confusing, which is why we recommend, when at all possible, to use EC and get an actual EC meter rather than a TDS meter, just for consistency. And so everybody kind of is on the same page and knows what we're talking about. And then the last factor we're going to talk about is nutrient levels. So nutrient levels are typically measured in milligrams per liter, which can also be defined as parts per million. That's going to be listed in the main body of our lab results here. That's going to take up the main chunk of it. And this measures the individual concentrations of all of the individual nutrients in solution. So on our lab tests, we list total nitrogen and then 3 forms of nitrogen, the nitrate, the ammonium, and the urea. And then we also list phosphorus, potassium, calcium, magnesium, sulfur, and all your micronutrients that you're going to need. The only accurate way to really know what's in your solution is to have your solution lab tested. So there are individual ion probes that you can get. So if you wanted to test just for your nitrate so that you know what's in your solution, you can do that. But to be able to measure everything all at once, that would be a lot of meters. It would get really expensive really quickly. So just sending in routine lab samples is going to be the best and cheapest way to, consistently manage your solution. So then transitioning to just getting started from the very beginning and looking at your water quality. What are we looking for when we look at water quality? What are we looking for whenever we go to make a fertilizer recommendation? So the main things that we're looking at are going to be the mineral nutrients that are already present in your water. Anything that's going to be really high that maybe we don't need to supply as much of in your fertilizer because you already have access to it. We're also looking at the sodium and chloride levels. Those are considered contaminants and will really determine if you have good or poor water quality. And then finally, we're looking at pH and EC just to get a good set point, help to determine whether you need a more acidic fertilizer, a more basic fertilizer. determine, which formulas are really going to complement your water in a way that you don't have to, micromanage it quite so much. So this is an example of really good quality water and really poor quality water. On the left, you'll see I've highlighted our soluble salts, our EC, our pH, alkalinity, and sodium. So the EC is fairly low. It's below 1. The pH is at 7.7, which is a little bit high. But like I said, for cleaner water sources, you're going to be sort of closer to that 7 mark. And then the alkalinity is relatively low at 67. One of the big factors that we're looking at is that the sodium is at about 13 parts per million, which is considered really low. So that's good. You're not going to have a whole lot of sodium accumulation over time. This water is pretty clean, and you could really have your pick of fertilizers at that point. Compared to the poor water quality that you see on the right, the soluble salts is starting to get up there closer to 1 at about 6. The pH is 7.5, which is fine, but the alkalinity is really high. You're at about 340 parts per million. And the sodium is well over 100. 100 parts per million is really one of those cutoffs where we start to be concerned about how much sodium is in your water. Over time, as you would use this water, the sodium would build up very quickly, and the plants would really struggle with nutrient uptake with that competing ion in the mix. So how does water quality impact your nutrient selection? Like I said, that's really going to depend on comparing whether you have a pure water source or a hard water source. For example, hard water sources that are higher in calcium may require less calcium from the fertilizer. So you could choose a low to no calcium fertilizer solution to really take advantage of the calcium that's already present in your water. High pH water sources may also require more acidic formulas. So, you can determine the potential acidity or basicity of a fertilizer formula. And if you have a really high pH water and you don't want to be adding too much just raw acid, like sulfuric or phosphoric acid, if you're limited in the number of fertilizer injectors you're using, something like that, then choosing a more acidic formula is going to help you to achieve the pH that you're really looking for. And then in that same vein, the high sodium and chloride content in your water may indicate that you need some sort of a purification system, like an RO system. If it's bad enough, you may even need to just find an alternative water source. So, if you have access to a different well or a tap water source, you are set up to be able to collect rainwater to supplement with some sort of a cleaner water source, then we may need to go that route. It's those kinds of things that you're really looking for. So this is that weird awkward break in the middle that I was talking about, where I'm kind of trimming my presentation down. So that was kind of the short version. I'm going to throw in some slides in there about lab testing as well. But now we're moving on to the long version. So next, we're going to move on to managing nutrient solutions over time and how that's going to be different in different types of systems. So in hydroponics specifically, there's 2 main types of hydroponic systems. You're going to have an open system or a closed system. We're going to talk about open systems first. So what an open system is a system where water and nutrient solutions are only applied to the plants once. So you mix all of your solution up in a reservoir, it goes through the system, it's applied to your plants, and then anything that isn't taken up by the plants is going to be drained to waste. It's not going to be returned. It's not going to be used again. So whenever you're managing nutrients in these systems and you want to see what the plants are taking up, you really need to be mindful of collecting some of that drainage formula. We call that runoff, and testing that, because as you can compare the fresh solution that's coming from the reservoir to what's running off, you can see what's remaining in solution, how the pH and EC change over time, and you can really use that to gauge what the plant is taking up, what it's using, and what it might need. Compared to closed systems, where after the nutrient solution is applied to the plants, it is returned back to the reservoir. So the same solution continues to recirculate over time. This is a really efficient system. It really increases your water use and your nutrient use efficiency, but it can make managing nutrients a little more difficult over time as, plants take up different nutrients and the ratios of nutrients become imbalanced, especially in automatic systems that are based on just EC set points and maintaining a particular EC. As I said when we were going over what EC is, just because you're maintaining the same EC doesn't mean that you actually know what sort of nutrients are going on in your solution over time. So maintaining an EC set point of, say, 2 isn't going to guarantee that your plants are receiving the same nutrients consistently over a course of weeks. So now let's talk about the effect of your solution pH on ion uptake. This is also important for whenever you're selecting fertilizers, as the forms of available ions in the fertilizer are going to determine how it changes the pH over time. So as plants take up positive ions, the pH is going to drop. And as plants take up negative charged ions, the pH is going to rise. So this is really going to determine, what the plant is taking up and how it affects the pH of its own root zone. So this is when we're talking about whether a fertilizer solution is acidic or basic. The forms of the ions present in that fertilizer are going to determine how it changes the pH. So like I said, nutrient uptake is going to affect the pH of the solution. As plants take up positively charged ions, it's going to lower the pH. Negatively is going to increase, which I know sounds backwards, but it's not. And then, so managing solution EC, like I said, the target EC for most hydroponic and CEA crops is going to be between 1 and 2.5, depending on the type of plant you're growing and the type of system that you're running. In general, basic bare bones rules: as you lower the EC, you're going to be lowering the nutrients present in your fertilizer solution. So as your EC drops, you're going to need to add fertilizer. Solution analysis in regular lab testing will reveal which specific nutrients are lacking. So if you were doing individual element mixing, routine lab testing would show you which nutrients you need to add back. Having an excessively low EC could lead to nutrient deficiencies just from general underfeeding, plants not receiving as much nutrients as they really require to maintain a consistent rate of growth. A high EC in your nutrient solution indicates that you have excess nutrients or you're starting to accumulate salts. So as your system recirculates and your EC is climbing, then you'll need to dilute with just regular water. But, that may not indicate that your plants are being overfed. If you have a poor quality water, it could just be sodium or chloride that's building up in the system and contributing to the higher EC. So this is just a quick example of a grower that I worked with a few years ago. This is how his nutrients changed over time, just to give you a visual example of how maintaining a consistent EC doesn't necessarily mean that your plants are being fed sufficiently. So whenever he mixed up his fresh solution, he had an EC of 2. He had nitrogen concentration in total of about 190 parts per million. And then everything else was fairly well balanced. The sodium was really low at 8 parts per million. He maintained that same solution at an EC of 2 for 3 weeks. And after 3 weeks, this is what his nutrient solution was composed of. So as you'll see, the EC is still relatively similar. It's a little bit higher at 2.2, but his nitrogen concentrations dropped significantly. So he started with 190 parts per million nitrogen, and after only 3 weeks, he's looking at roughly, let me do the math there, 60 parts per million. So that's going to be significantly underfeeding. He was growing lettuce, so he was definitely starting to see signs of fluorosis already, slower growth. And then you'll notice that the phosphorus, potassium, and sulfur and sodium all increased over time, a significant amount. So this is what was contributing to his EC and showing it as that still same around 2. But his plants weren't getting hardly any nitrogen because it was all these extra nutrients that the plants weren't taking up, they weren't using, and so they were just remaining in solution and continuing to recirculate through the system. So whenever you're managing nutrient solutions like this, it's important to check all of the potential causes of a nutritional disorder before you start to treat it. So like I said, he was starting to see nitrogen deficiency, but just adding more nitrogen to the solution probably wouldn't have been super beneficial because of all those excess nutrients that were also floating around in there. Other important causes to check are going to be your root zone pH. Improper pH can really impact nutrient uptake, especially of micronutrients. So if you're seeing a micronutrient deficiency, sometimes, like if you have an iron deficiency, adding more iron to the system isn't going to be very beneficial until the pH is fixed, because the plant won't be able to take it up either way. And then another important factor to keep in mind is nutrient ratios. Plants can only take up nutrients if they're balanced in a particular way. So for example, potassium, calcium, and magnesium, plants take them up in the necessary quantities a little bit better when they're balanced at a 4 to 2 to 1 rate, because all of these nutrients have very similar charges. the plant can't really differentiate one from the other. So to make sure that it's getting the proper amounts that it needs of each, then they need to be balanced in the nutrient solution. Same with nitrogen to potassium. We prefer about a 1-to-1 in most nutrient solutions. And then an overabundance of sodium or chloride. Those also have similar charges to necessary nutrients, and having them floating around in solution, plants aren't really going to be able to differentiate, and they'll take up the sodium or the chloride in place of whatever necessary element they need. Which brings me to the importance of routine lab testing. This can really help to avoid nutritional issues before they even really get started, and knowing what's in the solution can really help to make more intuitive nutrient decisions. For example, if plants are struggling with a deficiency, is the best route to try and add more of a particular nutrient? Would it be more beneficial to adjust the pH before adding anything? Or does the entire reservoir really just need to be replaced with fresh solution? Is everything just so out of whack that it's not going to help really to just keep adding things? And then, in terms of just general diagnosis, many nutritional issues have very similar symptoms like chlorosis, reduction in growth, and trying to correct a deficiency without confirming with lab testing that that's the particular deficiency you're dealing with can further exacerbate the issue. And then it can also help to rule out nutritional issues in the cases of, a pathogen problem. If you have a pest, environmental set points aren't quite right. For example, you can have symptoms of calcium deficiency, tip burn in lettuce, even though you're supplying adequate amounts of calcium. If the humidity is too high and you're not getting enough airflow, then it's not going to be able to pull the calcium all the way through the leaves, and it's going to present as calcium deficiency. So getting tissue tested in the lab is really going to help to rule out whether or not it's a supply issue or an environmental issue. And that's going to conclude my presentation today. If you have any questions, feel free to reach out to me.